Hello, everyone. Welcome to the second weekend of Beyond Bohm, Science, Order and Creativity, Physics and Metaphysics. I'm James Barbieri, Program Director of the PARI Center, and I will be your host for today. And as a host, I'm here to help you throughout the call, so any problems, technical or not, feel free to just send me a message in the chat. Before I begin, I'd just like to very briefly go through a couple of Zoom rules for today. First of all, we ask participants to turn off their microphone during the presentations and Q&A just to ensure a good quality audio. But at the same time, encourage everyone to turn on their cameras so we can see everyone's faces and reactions. During Q&A and discussion, if you want to ask a question or make a contribution, you can either use the raise your hand function on Zoom, which can be found at the bottom of the screen under reactions, or if you can physically raise your hand, and if I spot you, I'll call out your name. Or if you're feeling shy, you can always send your message in the chat and I can read it out for you. And finally, all sessions are recorded for archival purposes, but also for you all. As always, the recording will be available to you after 3 days after the session, so you should all receive the link to see this afterwards. And now we can begin this session. So today we have the honor of introducing Basil Hiley. Basil is a regular presenter here at the PARI Center, friend of our founder, David Peat, but mostly known for his work with David Bohm and his work following Bohm's death. Basil is the Emeritus Professor at University College London and winner of the Majorana Prize Best Person in Physics in 2012 for, and I quote here, his paramount importance as natural philosopher, his critical and open-minded attitude towards the role of science in contemporary culture. Basil's career has been long and successful, and we don't really have the time to go through all of his achievements. But if you know Bohm, you must have heard of Basil, as amongst other things, he co-authored with Bohm The Undivided Universe, the book we just mentioned, which is the main reference book of Bohm's interpretation of quantum physics. Basil is currently working on several experiments which may reveal and prove the hidden variables theory at UCL. Today, Basil will talk about the Dirac-Bohm picture, Bohm's 1952 approach in a wider context. And with that, I'll pass it over to you, Basil. Welcome.
Thank you, James. Welcome, everybody, to the meeting. I hope, having already had a warning about the mathematics in my talks, I'm afraid I'm going to put mathematics up because I'm going to talk about the physics. Now, the relevance of it was very nicely discussed by Giuseppe Vitiello in his talk last week, because what he was using there, the physics that he went through very quickly and very rapidly, is really the physics that lies behind some of the ideas I spoke about in the PARI meeting. What was it, about a month ago, wasn't it? Something like that. So what I want to do now is just to talk about the physics, and hope from Giuseppe's talk, you will see what it is to do with consciousness and these things that I know a lot of you are very interested in. I think, as I told you in my talk last time, I don't know anything about consciousness apart from being conscious or being unconscious. Okay, so let me get on with the physics. And I'd like to take the screen, if I may. Oh, that's brilliant. Everything rehearsed and it's gone wrong.
No problem.
Can you just be patient with me for a minute? Where's the... Oh, sorry, yeah, I've got it here in front of me. Okay, folks, can you see that?
Yeah, we can.
Can you see that? Okay, good. Let's go. So what I want to do here is to talk about the physics. Now, I already had a question of, do you have to read The Undivided Universe to know what I'm talking about? No, because I'm going back to go forward again. Because I've moved on quite a bit from where we left it, where David and I left it in, what was it, 1993 when he left us. And I've there's a few years gone on there, and I've actually done some new work, and I'm now looking at what Bohm did in a very different light, and I'm trying to get this across to you. So let's go back again, because most people have got the de Broglie-Bohm model wrong, because it started with de Broglie in 1927, his PhD thesis, where he was describing the behavior of the particle. It's easy to think about in terms of waves. This is the amplitude and this is the phase of the waves. But I want to change that attitude, and I want to say this is a field and this is another field. And it's these two fields together, two real physical fields, that give rise to quantum mechanics. This one behaves like a singularity, i.e. where the particle is, and this is a classical phase.
Basil, I'm very sorry indeed to interrupt, but should we still be seeing your title page?
No, you shouldn't. You should be seeing...
We're not. Well, that's all we're seeing at the moment. From the fact you were saying, you were obviously speaking about something we should be seeing on screen, but we're not seeing it.
What's gone wrong, James?
Oh, we're just seeing the first slide.
Well, I've already moved it on.
So maybe.
I've already moved it on. Do I have to? Let me try again.
Yeah, try again, and maybe try clicking rather than the arrows to move slides.
Okay, you think that might be the difference? Can you see the whole lot there? Otherwise, we'll have to go back to this picture, and I'd rather do this one. How's that doing?
Yeah, so at the beginning, try clicking.
I've clicked.
Oh,
No, we're just seeing your title page, the Dirac-Bohm picture with the nice view of the beach.
The technician told me what's wrong.
Try press the ESC button.
Yeah.
And maybe try play from the beginning of the slideshow.
Where is that?
It should be along the top of the toolbar. Instead of just playing slide, play
okay. Play slideshow. You think that'll work?
Might do. We can't see your screen at the moment.
Okay, sorry about this, folks. I've got to go out again. Share screen. No, I don't know how this works.
Perfect now, yeah.
Is it working now?
We can see it.
Wait a minute, play slideshow.
Yeah.
Has that changed?
It's still the first. Try pressing the arrows or the click, or maybe the
click
button.
This happens frequently in Zoom, and I think we always have to go back just to see it without the presentation mode.
Oh,
well, at least when it happened. Yes. Yeah, like this. Yeah. So I think this is maybe the only.
Yeah.
Well, this has never happened to me before.
We are now seeing your third slide, Basil.
Yes, I know. I'm sorry. It's not my third slide. The real difficulty.
Number 3 on the.
Okay, we'll have to go this way. We can't waste any more time. So now let me see. Where was I? Oh yeah, we're going back to see de Broglie. I'll have to take you through. Can you see my cursor moving?
Yes.
Okay, good. I got as far as here. Now, the second part of the story is that in the original paper, de Broglie was actually looking at the dynamics of the individual. And he actually found that an extra term, which we got as the quantum potential in Bohm's way of looking at it, changing the rest mass. So the extra energy that involved in the quantum potential actually was associated with the change of the rest mass in the de Broglie theory. Then he was invited to the Solvay conference in 1927, and because he was finding very difficulty in understanding the nonlinear equation that involved R and S, he presented what he called the pilot wave theory. And then look what it says about the pilot wave theory. I contented myself with the presentation of my ideas in an incomplete and diluted form, which I called the pilot wave theory. And then a bit later in the same book, that's this book, Nonlinear Wave Mechanics, he writes, so I saw clearly that the pilot wave theory could not supply the interpretation I sought. Okay. Then we go on to David Bohm, his 1952 contribution. And now the interesting thing is there is a prototype of the Bohm approach in Dirac's classical book, The Principles of Quantum Mechanics. And it's in action in section 31. And I know David Bohm refers to this section in his book on quantum theory. And I wondered whether this was not the inspiration for what he did. But Dirac does it in a very different way from the way Bohm did it. So then Bohm worked this out and he published it, and he called it a suggested interpretation of the theory of quantum of hidden variables. Now, actually, it's got nothing to do with hidden variables. There are no hidden variables in there at all. You use all the formulas of standard quantum mechanics. But because he introduced the idea of hidden variables, he walked into trouble. Why did he walk into trouble? Because von Neumann had already proved a theorem that said hidden variables would not work. Now, interestingly enough, and I think Maureen, I think you sent me a second copy of this paper, which I found earlier on from Professor Drizet. And if that's the right way to pronounce the French name, I'm sorry, it's probably Drizet. And what he said was, I found an early version of the Bohm paper in de Broglie's old papers somewhere in de Broglie's room or in the de Broglie archives. And it was entitled A Causal and Continuous Interpretation of the Quantum Theory. If only he had used that title rather than walking into the trap of hidden variables. And having said that, please note that in Causality and Chance in Modern Physics, he then reanalyzed his earlier work and he said, the interpretation I proposed does not go deep enough. And then the whole section, and in fact, the whole chapter of chapter 5 of this book, we must go beyond mechanism. Now, both these authors were saying, look, I don't believe that early simple stuff, yet we find the de Broglie-Bohm model has morphed into Bohmian mechanics. And when Bohm saw that, he said, have they not understood a word I have written? Right. Okay. So the reactions of the 52 paper were, Bohr was angry with Bohm, Pauli ridiculed a guiding wave of kindergarten children being led by a teacher. Oppenheimer, when confronted, said, can't see anything wrong with it, but let's just ignore it. That was David Pete found that in his researches for the biography that he wrote. And Rosenfeld wrote that there is no, listen to this, there is no book that one can refer them to, and I presume that's you and I, and that would protect, he wants to protect us from the confusion created by Bohm, Landay, and other dilettantes. I have never seen such a criticism in a science paper in my life before. And Einstein just said he got it too cheap. And in the sense, I agree with Einstein, because what Bohm did was something very simple. Okay, so the story I want to unfold is this quantum potential energy, because we see it left, right, and center. People say, oh, ignore it. So what is the origin of this quantum potential? This is really the aim of my talk here. Well, both de Broglie and Bohm noticed it was a new quality of energy. And since Schrödinger's equation is a conservation of energy, you can think of Schrödinger's equation simply as the total energy is equal to kinetic energy plus the quantum potential energy plus the classical potential energy. And if you were a classical physicist, that term would not be there. So what quantum theory or quantum phenomena do is to introduce a new quality of energy. Okay, new quality of energy, is that crazy? No, because we have things like the Helmholtz free energy, the Gibbs free energy, the heat energy, and so on and so forth. There are many different qualities of energy. Now, the earlier discussions did not dismiss the quantum potential as a load of rubbish. Madelung used it in his hydrodynamic model. Fritz London, who very famously contributed to our understanding of liquid helium, uses it. Kennard uses it. Enrico Fermi, who I'm sure most physicists, most people in the audience have heard of, he used it. Carl von Sacker actually used it. And even Feynman used it. And if you look at the lecture notes, the famous Feynman lecture notes, volume 3, you will find this written: an additional term containing, when he was actually working on superconductivity at the time, or lecturing on superconductivity at the time. And he says there is an additional term which contains a factor h bar squared. Look, there it is, h bar squared, which we call, which we could call, as almost as if he's just discovering it, when it was well discussed by these earlier workers, a quantum mechanical energy. And then he adds later the additional force, which the gradient of some mystical quantum potential. He then says, well, actually in the middle of a conductor, superconductor, it's negligible. And that's all he says. And then there was silence. So the real question is, and I think this is the problem, people have said, oh, there's something wrong with this energy. Because all these guys are big guys in physics after the war were actually dissing it. So where does this come from? Why does it appear? Okay, now what Dirac did, sorry, I'm finding it difficulty, please bear with me. No, I've got it, because the thing's not working properly, I'm having a difficulty. Okay, right, now, Bohm used the standard formalism. He added nothing new to what he did. He simply did what all A-level mathematical students are told to do. When you see an equation with complex numbers, split it up into two real number equations. So what's the problem? Actually, there is no problem. What people seem to have forgotten is the very basic Stone-von Neumann theorem. And what that says is that the Schrödinger picture is unique only up to a unitary transformation. That means that you don't have to stay with the Schrödinger picture with all its waves. There are many other mathematically equivalent pictures. Well-known ones, Heisenberg picture, the interaction picture, the Feynman path method, Fock space picture. They're all different views mathematically coming from the same formalism. And what Glenn Dennis and I wanted to do when we were going through that was to say, let's explore the possibility of a new picture. And this wasn't us doing it. We actually read Dirac's account of in that section 31, and we found, blooming heck, he's presenting another picture. And as I say, Dirac almost beat Bohm, and what he did was to introduce a non-commutative phase space. Now, I'm sorry to use this big word non-commutative, but all it means is that all you guys have always got a product of two things, which it doesn't matter which order you multiply. 2 times 3 is the same as 3 times 2. But in the non-commutative phase space, the products do not, the inverse product, sorry, the products do not, this thing does not vanish. In other words, these two products are actually different. And that's a bit hairy for Dirac. He admits it when he saw this in probably the 30s, because his work goes back to the 30s. Okay, so what did Dirac do? He said, oh, I'm not sure I can deal with non-commutativity. So let me do a series expansion in powers of h, so I can keep track of classical physics, because when h bar equals 0, the feeling is that you get back to classical physics. That's not correct, but let's play that game. So what he found was he only got Bohm's first equation, which is just a conservation of probability, but not the second. And the second one is the one, look, it contains h bar squared. And if he's only going up to powers of h bar, he's not going to see this term at all. And so what he obtained was this classical equation, well known, no quantum potential, the classical Hamilton-Jacobi equation, and then he gave up. And I never quite understood why he gave up. He says because he thinks somehow Heisenberg's uncertainty principle will be violated. It isn't. Anyway, notice that we have two equations, this one, and they're to do with these two fields that de Broglie wanted to make into his double solution. And I will always be concentrating on these two fields as real fields. Okay, so then what we thought was, all right, let's follow Dirac. And since Bohm got it from expanding in terms of real and imaginary parts, let's call it the Dirac-Bohm picture. How does that come about? Well, in the Schrödinger picture, we have the energy, the Hamiltonian, in terms of position and momentum as operators, and we have a wave function. Now, in the Heisenberg picture, what we do is we put all, we do, this is what's known as a unitary transformation. You don't have to know how it works. I'm just pointing out, it puts the Schrödinger Hamiltonian in there and gets what I call the Heisenberg Hamiltonian, which is a function of time. You then look at the operators that, or the Q numbers, the X becomes time dependent and the momentum becomes time dependent. So you can really throw away the wave function. You can do everything in terms of the operators themselves. Now, what the Dirac-Bohm picture does, it introduces this unitary transformation, where this is the classical action. And this is exactly what Feynman does in getting his famous interpretation, sum over paths. He does the same thing, only in a different way. What we did was to follow this, and we found that the operator becomes time dependent, but it's the same as the ordinary, so it doesn't have time dependence in it. And the momentum actually has changed. And the momentum becomes the Schrödinger momentum minus grad S. And those people who know about the Bohm theory, this is just the Bohm momentum. So why is it coming in there? It's a very strange place to come in. Then what you do is you want to find the evolution of a wave function. I'm still using wave functions here. You then use this equation, and out pops the two equations that you saw on the previous slide. Out pops this equation and this equation. Okay, so you get it. So now what are we saying? This is mathematically equivalent to the Schrödinger picture. So you will never get any different predictions for experimental results using this method as you will that method. So all those people who have spent years trying to show that the Bohm theory is wrong, it's not wrong. It's just another mathematical picture of the same problem. Now, does it tell us something new? Well, we've seen the things that it does tell us, but I want to know, what about this quantum potential? Where does that come from? Oh, God. Is that the next slide? Sorry, can I? It really is a menace not being able to do it the way I always do it. Okay, so then, like all potentials. It produces a force, but what does the potential look like? And Chris Dewdney and Chris Philippides combined to get this beautiful picture of the quantum potential for the two-slit experiment. For those who haven't seen this before, the two slits are there. So we're looking at the electrons coming from two slits in the screen, and no electrons arrive here, and the electrons travel on the top of this potential. And so what you see is the fringes. Here we've written down the trajectories using the potentials generating a force, and these are an ensemble of trajectories of individual electrons, and they arrive at the screen bunched up as if they were behaving like a wave. So there is no wave effect here. The individual, the wave is an ensemble. We've got the individual trajectory and we've got the ensemble. So it's really a way of combining the individual with the collective. And that's something that David was very interested in. It came out of his plasma work. Okay, so let's look more closely. Sorry, I'm still following this. Where is the quantum potential coming from? Okay, well, now I want to go back and I want to tell you something which utterly surprised me when I went through von Neumann's paper, this one in the Annalen, I don't know what the German translation of that is, but it's in German, and it's the, I'm not going to pronounce this either because I'm not a linguist. This is the uniqueness of the Schrödinger operators. And in that paper, he proved this theorem that we're talking about, but the way he did it was quite extraordinary. He introduced an algebra of quantum numbers, and what he found was that he had to introduce a new product, and he created that new product, and that new product is the product that I've been saying, the non-commutative product. And to cut a long story short, the non-commutative product is a star product, and it gives us the Heisenberg relation, and the star product takes the form. Now, I know, sorry for people who are not mathematicians, but I just want to point out something. This is quantum mechanics, and this thing here appears in classical physics. It's the croissant, a classical Poisson bracket. I love a croissant at the moment, actually, a classical Poisson bracket. So what John von Neumann proved in that paper was more than the uniqueness, more than uniqueness up to a unitary transformation, but that there was an isomorphism. That means a one-to-one correspondence between quantum operators and Q numbers. And the Q numbers satisfied, they could just treat them as positional momentum, but make sure that the product is this product. Now, I'm not going to show you how to use this. It takes a little bit of getting used to, but please, that's not the point I want to make here. What I want to make here is that quantum dynamics can be completely formulated in a non-commutative phase space. And this algebra is called the Moyal algebra. Why? Because von Neumann's algebra was rediscovered by Dutchman Groenewold and by New Zealander, Australian Joe Moyal. Groenewold in 46, just after the end of Second World War, and Moyal in 1949. And in Moyal's paper, the Bohm theory appears in the appendix yet again. So you see there's a long history, and what David did brilliantly was to bring it out clearly to show, look, this is what is going on. But somehow people ignored all this background, verifying what Bohm had done, and had to try and prove he was wrong for some reason I could go into, but I'm not going to because I might get it wrong. I don't know why people just objected to it. Now, I just want a little aside here, which is not very important. So if you want to switch off for a minute, switch off. In this non-commutative bracket, as a non-commutative product, there are two types of brackets we can use. We can use commutator brackets, or we can use anti-commutator brackets. And what one finds is, or what I found, which absolutely staggered me, was that I said, well, how can you do this for the Bohm approach? And what I found was that if we use the Baker bracket, BB, the Baker bracket, in other words, if we use this anti-commutation relation, we got the Bohm momentum out. And if we use the Moyal bracket, we got another momentum out, the osmotic momentum. Why do I call it osmotic? Because Nelson tried to generate the Schrödinger equation from a purely stochastic point of view. And in stochastics, you get things like osmosis. And he called it an osmotic momentum. And David and I just followed him, calling it osmotic momentum in our paper, which I didn't put the reference to there. Okay, forget the mathematics. Pictures, most important. Pictures are more important than anything else. Here is the two-slit experiment. These arrows are the Bohm velocity arrows. But look, this Bloch and his co-workers actually showed what the osmotic momentum was doing. It was pushing as if it was keeping the particles where they bunch on the screen and sweeping it away from where there's no particles on the screen. So there's some dynamical process going on underneath this. Okay, now, and there's no waves. It just looks like a wave because it's the collective that's the wave, not the individual. Okay, so what are we doing? Why two momenta? Well, if you go through the classical way of taking the Lagrangian and minimizing it, and for those people who are not mathematicians, this is boring standard stuff that you learn, undergraduate physics, postgraduate physics. You take the Lagrangian, you take the kinetic energy, and you subtract off the classical potential energy, do a magic trick, and you get the classical equations of motion. Heisenberg showed that if you did the same thing by creating a Lagrangian in terms of the wave functions, you can get Schrödinger's equations out. And if you do what Bohm did, was to write R and S, you find the Lagrangian splits. This kinetic energy splits into two parts. This is the kinetic energy that arises from squaring the Bohm momentum. And this is the energy that arises from squaring the osmotic momentum. And just to double check, when you've got a Lagrangian, you can get the energy momentum tensor, and you find that you get the two terms again. So I'm now going to declare that there is no ontological wave function. There is only the dynamics, and the dynamics is in terms of the two fields S and R. I'm sorry, I'm creating heresy, but I'm so old you can burn me at the stakes if you like. Okay, so now then, okay, but wait a minute. You can't throw the wave function away. You can't throw it away, man. No, you don't throw it away. All the information that is contained in the wave function is already in the algebra. It's in an element of what we call the left ideal. I'm sorry, I've got to use this word here because I don't know where else. It's in the algebra itself and in a very special place, which we mathematicians can actually identify. And all the information in the complex conjugate are in elements of a right ideal. So they're already in the algebra. Okay, so if we look at that in terms of the Schrödinger equation, here we are, that's G0, but that's just R, and G1, that's just S, and E is I in this case. I'm sorry, I've changed the notation, very naughty of me, but I couldn't be fagged to redo the whole slide. Right, but then if you go on to include spin, this is when you get the big payoff. And this was when I was able to show that the Bohm theory can actually be generalized to include Pauli spin and can be generalized to include the Dirac equation with a relativistic spin. And that's all done in that paper there. And I couldn't have done it without going through the algebra. And these are the Pauli spin matrices, are formed from the Pauli spin matrices. They just happen to be quaternions. They're isomorphic to quaternions for those people who like collecting names. And these are the gamma matrices that everybody in physics knows all about. They're made out of products of pairs of them. And this gives rise to the biquaternions. And did you know that there's a man called Willard Gibbs, who was a professor at the university I am now have the honor of belonging to, University College London, who actually obtained these objects from classical mechanics by generalizing the way you look at classical mechanics. And what I'm doing here is really sitting on his shoulders, and he's carrying me through so that I can confidently introduce these ideas here. Okay, and the reason why we have this we need more information if we're going to take the relativistic spin. So please, folks, if anybody says to you, oh, Bohm's theory cannot be used in the relativistic domain, tell them they've got it wrong. It can be. Okay, so let's go on. Now, no wave function. Okay, look, how do you account for this brilliant picture made by Peter van Rieth? The way, remember the Stern Gerlach, for those people who don't know about it, is the way you split a particle which is spinning into spin up and spin down. And what we have here is the magnetic field is actually trapped here. It's an inhomogeneous magnetic field, so that it pulls the two particles, the two states of the particles apart. So this will be upside up and this is upside down. But look, when you look at the dynamics, the spin doesn't immediately jump into the up state. And there's no field here. The only field that is here is the quantum potential. Just think about this. There's no quantum jumps in this story. There are no quantum jumps. It just goes through smoothly. Okay. So you see why I'm sort of heresy. It really is heresy. Okay, now then. Oh, you're out on your own, BJ. You don't know what you're talking about. So I thought, well, we've already heard that Feynman has this approach to Feynman over sum over paths. And he uses an e to the I s. So he's doing some exponential. Surely there must be some relation between these two theories, the Bohm theory and Feynman paths. And there are. Now, if you look at the Feynman paths, what are they telling you? They're telling you that their derivatives, this is just d by dx for anybody who's even more confused over mathematics. Now, how do you derive a derivative? A derivative is you want to get to x, and you're coming from cap x, and you're coming from little x, and you ask, what is the speed, if you like, if you don't like derivatives, what is the speed of the particle going between these 2 points if it takes delta t? Well, all you do is you just take the difference and divide by the difference in the time. And then the forward derivative, that's the speed going forward. You take, now you put x prime minus x divided by delta t, and you find that these two objects are not the same. So you have a forward velocity and a backward velocity. And if you calculate the mean drift forward velocity, it turns out to be the Bohm velocity. But if you take the difference, it becomes the osmotic velocity. And what people now do is they make the complex field of velocities. And so what we do, what we note here, by the way, sorry, I must put this in, very important for later on, and that is time invariance is broken, and Giuseppe Vitiello was talking a lot about broken symmetry in his talk. His idea of the double comes out of broken symmetry time reversal. And therefore what we've done here, I just thought I'd put this in here for Joe Roger, that he is always in his works, in his brilliant work he does, is always calling for a complex space-time. So this is somehow also calling for a complex space-time, but in a very different way. Okay, now I'm definitely not going to go through those. If anybody wants to see the mathematics, please look at the recording. It will be in the recording, James. James, will it be in the recording?
Yes, of course it will, yes.
Okay, so then they can read it at their own leisure. You don't need it. Okay, so now let me, sorry, folks. I did something there that I shouldn't have done. Okay. No, I can't. I don't. This damn thing is. James, I'm going to have a word with you afterwards. Okay, now let's go on to this next slide. Sorry. Where does the quantum potential come from? Was the story I'm telling, and it comes from gauge fields. But of course, you don't know what a gauge field is. But just remember gauge fields. The physicists will know quickly what I'm talking about. But those who don't worry, I'm going to tell you what it is. Now, and it's very important because this is where ferrometry comes in. I think I used the word in the abstract. So normally classical forces are assumed to arise pairwise additive. So you've got two particles and there's a force between them, usually the inverse square law, and they pull together and that's it. And Newtonian's gravitational forces arise in that way. But Einstein, in his general relativity, said that was wrong. You've got to modify it. Okay, stack that aside for a minute. And now come back to Feynman. Now for something completely different in the Monty Python scheme of things. Feynman introduced what he called, and I don't think it's due to him, but he talks about minimal coupling. And that's where I learned it, so I'm going to attribute it to Richard Feynman. The P is written like this in quantum electrodynamics. So when you're bringing in electromagnetic effects, magnetic fields, electric fields, this is the vector potential. So you introduce this momentum by writing it as minus E over C means negative, it means the charge on the particle. And notice the Dirac-Bohm picture replaces, that's interesting. It replaces the vector potential with this other vector, which we've been calling the Bohm momentum. So the Bohm momentum is actually the same type of thing that the electromagnetic potential is. And now came the crux, which really excited me, was when I looked at Maurice de Gosson's book, that's that one there, he talks about Coriolis forces. And he shows that you can get the Coriolis force out of exactly the same change in the momentum where you introduce this vector potential. R is the center where the man is standing on the Earth's surface. Remember, Coriolis forces are the things that make us so wet in this country. They come off the Atlantic, and because the Earth is rotating, it rotates the atmosphere, and then we get our beautiful depressions. So these Coriolis forces don't come by any activity between pairs of particles. And you know all about this if you've had kids or you've actually been a kid, because if you sit on a disc, when it's stationary, you can throw a football across to each other, no problems. If someone actually starts the platform rotating, you can no longer do it, because if you throw it, this guy's moved, the ball will arrive here, but you've moved on. So you've got to have the trajectory to reach that man has got to be curved. Okay, but that's just a movement effect. No, listen. In quantum mechanics, we make P is equal to this derivative. Now, in general relativity, we use a covariant derivative. And in general relativity, it tells you that when the light ray goes past the sun, it is bent. The sun is not rotating, but what did Einstein tell us? Einstein told us that an accelerating disk, an acceleration, is equivalent to a gravitational field. So you can't distinguish between these two. So what have we got? We've got something very interesting here. And we'll see in a minute that this is where the quantum potential comes in. It's not one of these forces. It's a force which arises out of this. It's a Coriolis force. Now, wait a minute. Okay, so what we're talking about here, remember, is momentum. We're talking about connections. We're talking about movements. We're not talking about pairs of particles attracting each other like a couple of love-struck kids. We're talking about movement. How does force arise out of movement? Well, what we've been doing, we've been changing. Geometry is with C numbers, but the non-commutative geometry is Q numbers. So the geometry and the dynamics co-determine each other. And this is why Einstein introduced the word phronomics to describe this change. Is this a new word? No, actually it's a very old word. It was used by Leibniz, it was used by Kant, who are both philosophers who everybody surely has heard of. And it was used by Günter Grassmann in his discussion of Grassmann algebras. And it's used in musicology. And I visit Helsinki to talk with my friend Paavo Bulkinen, who's going to talk tomorrow. And there was a young student, it wasn't young, he was a student writing a PhD thesis. And I said, oh, hello, how are you? He said, I want to talk to you. I said, oh, yeah, good. And he was working in the musicology department in Helsinki. And I thought, the guy's mad. What does he want to talk to me for? I know absolutely nothing about musicology. You know, try and play I can't even sing in tune, let alone become a musician. But then he explained it to me. Okay, so now then we have to go back to the origins. And we always go back to Greek. Kinos, that says kinos, kinetic. So we got our kinetic energy from the idea of kinos, and that's the idea of the cause of motion. So the motion has to have a cause. You got to push it to make it move. But the Greeks, clever blokes, they have another word called phoros. And phoros is the idea of mere going with no reference to a cause. And if you want to see a brilliant discussion of this, I had to go back to 1892. I'm always up to date with my research, by the way. 1892 to find a discussion of this. So anybody at the turn of that century would have known this word. But of course, if you look it up in Google, it doesn't exist. Okay, so now then, how do we generate force? Well, it's blooming obvious, isn't it? If you've ever thought about how we stay up in the air in an aircraft, we have a force lifting us up there, but it's not someone downstairs pushing us up. It's the difference in the rate of flow over the wing, under the wing. And that gives rise. So the difference in flow gives rise to the force. So we've got to be something which is not a local entity. And now for all cricket lovers, I knew this when I was at school, by the way, you realise, because I pretended that I was going to be a fast bowler and play for England. Dream didn't last long. So I knew the theory of the spinning ball. So there's your cricket ball spinning. And if you have to be a batsman, you can make the ball curve. Baseball, the same thing. And it's due to the Magnus. It's due to the thing that gives the Coriolis a force. It's due to the appearance of this P minus A term in the momentum. So the movement has its origin. Is movement the origin of the quantum potential? Is movement the origin of the quantum potential? Okay, now let's have a look. You might be a little bit worried. How's the time? I'm sorry, I'm going a little bit over. Is everybody happy? The stability of Bohr orbits. Remember, we actually put waves in and put standing waves, and we managed to get that n. But there is another way. And that is done in David Bohm's book. Sorry, the reference is not here, in his quantum theory book, where he shows that going a little bit further back in time, when the Bohr-Sommerfeld quantum conditions were discussed, you found that the energies of the same n, but for different orbital angular momentum, were all the same. And that only works in a Coulomb potential. And Bohm shows that in his book very, very nicely. So if you don't have a Coulomb potential, the orbits actually precess. But please, this is Mercury. Look, I don't know what, look, how about that, James? Italian, Soleil. I can't read that. You will tell me what Mercury is in
Mercurio.
Right, thank you. Sorry, it's just I got it out of Google. It was in Italian and I couldn't change the name. We're international here. So in this case, this deformation was a confirmation of general relativity. So it was a confirmation of the curvature of space-time. But look, it's simply deforming the space. So could this be something connection? Are these connected? Interesting. Okay, now then, I'm on the last lap home. Yeah, I'm nearly there. Take a deep breath, folks. Gauge fields. Remember, we had a problem with derivatives. That if we had a derivative or a velocity going from there to there, it was different from the velocity going from there to here. But the Bohm velocity is integrated over all these different velocities. It's a mean velocity, and it gives this velocity here. Now, how do we see this, and how is this connected with Vitiello's? Well, let's connect them by saying we've got a wave function here, psi of x, a wave function here, psi star of x prime, and between them we define essentially this object, which is a propagator for those people who like to collect names. It's the propagator. Now then, what we find is, and what inspired me here was reading Richard Feynman's Reviews of Modern Physics paper. That was his thesis, by the way. I only read people's theses. They're much more interesting. By the time they get all formalized, it's designed to confuse everybody. And what he said in the thesis was, I'm going to think about the wave function as information coming from the past. And I'm going to think about the complex conjugate as wave function, as information coming from the future. And this was my forward derivative and the backward derivative. Now, it's not coming from, I would rather put it anticipating the next step. If it's a straight line, you just keep going. But if you've got this jig-jagging going on, you don't quite know what the next step is. And this is, in fact, where Vitiello's double comes in, because he had these two equations. I'm replacing x plus is my x prime, his x minus is my x here. So what he's done is he's got his effective Hamiltonian is a double. And he then uses these ideas for his interpretation of using, sorry, his interpretation, his way of looking at quantum theory to explain consciousness, his view of it. Okay, now then, last step. Now I want to go back to something which you may think I've forgotten, and that's the Aronoff-Bohm effect. Remember, what you do there is you start with the Hamiltonian, which again, I've just put C equals 1, so that C has disappeared because it's equal to 1 in this notation. We mathematicians change notation, you know, pretty rapidly. You have to keep up with us. So, okay. And then if we solve that Schrödinger equation with that Hamiltonian, we can write it in this form, where this S is an integral over A dot dx. So if we have two paths, we've got S1 and S2. And the reason why I'm putting the two paths here is because the Bohm-Aronoff effect is the following effect. You've got your two slits, you put a magnetic field in a very small confined region. You can even put a superconductor around it so there's no field outside. And then when you look at the interference pattern, if you've got a current flowing in that solenoid to produce this magnetic field in this shielded region, the fringes shift. And in fact, if you look at the phase at Q, it's the phase difference, remember, that gives you the zeros. When the phase difference is 0, nothing arrives there. Okay, so the phase difference now is going to be the difference of these two, which is then an integral round. It's the same as the integral round the circuit, and you find that doesn't vanish by the Stokes theorem, and that gives you a value of the flux. So it doesn't matter that the electron cannot see the magnetic field. Everywhere else the magnetic field is 0. It's still affected by it. And I take you back to the Stern-Gerlach magnet that Peter van Rieth had that beautiful calculation for, where he showed that there was turning when there was no magnetic field present. And then in the experiment, what you see is this, and here are the trajectories, and you can see they're just displaced. Okay, good. Now, where am I? Here we are. Okay, now then, the main theme, I'm sorry it's been so long getting here, is broken gauge symmetry. So having told you what gauge symmetry is, I'm now going to break it. And I'm going to tell you this breaking is the key to everything. I once went to a seminar given by, I think it was T.D. Lee. Now, these are a couple of American physicists, Lee and Yang, who got the Nobel Prize for parity non-conservation. And Lee was talking about, it must have been C.N. Yang. Sorry, you guys, if you're still with us, I can't remember who it was, but once you get a Nobel Prize and you're coupled, you're never uncoupled again unless you study the subject in great detail. Anyway, this slide came up. It's a symmetries. Everybody thinks symmetries are beautiful. No, they're not, he says. And up came a slide of Venus de Milo. There you are, broken symmetry. That's where the beauty lies. Okay, I don't know whether that'll work with people, but broken gauge symmetry is what we're looking for. Look, when de Broglie had his problem, he said, I replaced the particle by a wave. But if it only has one momentum, a unique sharp momentum, it's a wave which goes from infinity minus infinity plus infinity. Where do you put the particle? If you notice in this theory here, look, that is always treated to be the same. But suppose we don't, this is a dynamical variable, suppose that changes for some reason or other. Well, you can break the symmetry with the amplitude. You can break the symmetry with the amplitude. And if you look, so we've broken the transition. So this is the second break of symmetry that I've used. Number one is breaking symmetry in time. And now I'm breaking symmetry in direction. And so what I've got is something I don't know whether you can read that on your screens, but that's e to the minus x squared over 2. It's a Gaussian. So the R is a Gaussian in this case, and he's got a sign, and I can't read that myself, I'm sorry, but there's a phase there, which is a sine phase, and it's a function of t. So there is the image, the quantum image. That's the nearest you can get to the image of a particle. Therefore, when we're talking about quantum mechanics, we're not talking about particles as little billiard balls. We're talking about process, not a particle. And it's a process, but it's a localized process. Okay, so now what points do I want to make from this? Well, I want to say now, this is why Vitiello needs 2 points, because he's talking about regions in the brain of coherence. And this is where his double comes in again. Maurice de Gosson, my dear friend Maurice, talks about quantum blobs. And by the way, I encouraged him to say that after watching a television program with my kids many years ago, where I can't remember the actor anymore, or the guy who did it, Mr. Blobby. And the name stuck. He liked the name very much, so he calls them quantum blobs. And they are regions of phase space, which you cannot get inside. And that leads to a very interesting idea of the no squeezing theorem, which I don't have time to talk about. Now then, I want a second point, having shown this. We've now got this localized in space. Now I want to go back to the Fritz London paper that he wrote in 1927. And it was in Zeitschrift für Physik, and you've got it, it was in German. But it's now been translated. And in there, he's got a quote, in the Weil theory, and here we come to Weil, and I was talking with James about Weil, because Weil was very interested in Fichte, and very interested in Fichte and Schelling. And notice that Fichte and Schelling, going on to Hegel, which is what Bohm was very interested in, was really talking about process, not particles, and not particles in space-time as classical, but where you can actually create space-time from a process. So you don't start with a priori given space-time, but you start with process, and from process you abstract out space-time. Okay, that's an aside. But London was very interested in Weil's theory because it was to do with gauges. But you have to modify the gauge that Weil introduced, because you get into trouble if you use it in the form he used it. London did actually get round the difficulty that Einstein objected to with Weil's phase. And what he says here then is, in the Weil theory, one could justifiably think that in empty space, the measure could be influenced only by the electromagnetic field. One must now take into account that the old distinction, I hope I can read this carefully, the old distinction between impenetrable matter and the void, and please, the English translation has got this word wrong. This is Greek for void. It's got a new at the end there, which completely threw me. So with the void, oops, is completely removed, and that one is always in the interior of the all-pervading new substance. And he was looking at the wave function as the substance. So this is the wave function, if you're using it in the old language.
Good morning.
This is the old language. And sorry, good morning to whoever that was who interrupted me. It is there's something going on in that space. So already in 1927, we had this idea of what was going on in the space. Okay, now then, the final slide before I come to conclusions. What are the consequences of this? broken symmetry? Well, you need zero rest mass particles, but don't worry about that. They are the particles that Giuseppe talked about. They're the corticons in the Umezawa theory. They're the phonons in solid state physics. They are the magnons in the magnetic theory physics. But what the broken symmetry does is to change the ferrometry. And it does it by actually changing the metric tensor that you use. Remember, Einstein's vacuum is filled with the metric tensor. And it's filled with the metric tensor such that it's a conformal invariant, and we can identify that conformal invariance with this e to the sigma. And remember, I introduced e to the sigma in the amplitude, and it's related to the square root of the probability density. So the amplitude of the wave is actually coming in from the ferrometry as a conformal factor. It's got nothing to do with waves, it's the dynamics. The wave is just a brilliant algorithm, as Niels Bohr said it was, of calculating things. It's not the way you do your ontology. Your ontology, you have to take the real fields for the spinless particle is just R and S. So then if you look at the relativistic version of the quantum potential, you find it works out like this. The details are done in Delphinich, a paper which is not published. It's on the archive. There's nothing wrong with it. It's a brilliant paper. It's a bit hairy in places, but it's a brilliant paper. And it shows that the ferrometry has a curvature in it. This is the scalar curvature. So if you don't want to think about it as scalar, as changing the geometry, it certainly changes the ferrometry by making it into a curved space. And when I was doing this, I actually had some reason for going back and looking at Bryce DeWitt's dynamical theory in curved spaces. I had read this in the 1970s and completely lost in the morass of formulae that he has in that brilliant mathematical work that if you're patient and you can spend 3 years on it, you will find that he actually obtains exactly the same result for the propagator. Remember, we were talking about the propagator. He gets it through the propagator, and he shows that from the Feynman path integral point of view, this scalar potential actually appears. But most people doing high energy physics are not interested in geometry. They're interested in calculating scattering cross sections, quite rightly. Okay, so now what I'm saying here is we have a completely different answer to the question, what is a quantum particle? What it is not is a little hard billiard ball. What it is a region of energy, a localized region of energy. And this is very much related to the capacity idea introduced by the no squeezing theorem, particularly by Maurice de Gausson. And therefore we now understand, or we begin to understand, why the mass can be regarded as changing, because this is the effective mass of the blob. Now, is this total fantasy? No, because the high energy physicists who do scattering, who've tried to see what the proton looks like with their high energy machine, they can't do it in the lab, they've got to go to CERN and whiz things round in diameters of a few kilometers. And what they find is the proton consists of only 2% valent quarks and 98% C of quark antiquark pairs. So you've got something bubbling up inside the proton, this continual flux creating quark antiquark pairs. And that fits much better this idea, although of course we've got to dig much deeper than the simple ideas I've expressed to you now. Okay, man, I now hope I've shown you where to look for where the quantum potential comes from. So let me just summarize. Sorry, I've gone over a little bit. I hope you don't mind. We've reviewed the physics underlying the Bohm-Dirac model, and we've shown that it discusses quantum dynamics of a particle, which I can now put in quotes, using these two fields in the spinless non-relativistic particle. It's not a pilot wave. R and S both carry momentum and energy. By going back to the origins of the quantum mechanics, we find that the Bohm theory is actually Dirac-Bohm picture. So it's equivalent to the Schrödinger picture. And it introduces a star product. And that star product is related to the Poisson bracket, so we can see how quantum theory and classical physics can be related in a new way. Got nothing to do with h bar going to zero. If you put h bar going to zero, the whole thing blows up. We showed the relation of the Bohm trajectory very, very briefly to the Feynman paths. I've got a paper with Rob Flack, which does that much better, much more detail. Then we examined gauge forces and found that the Bohm momentum is a gauge field. And using gauge fields, we used the Bohm-Aronoff effect to replace the geometry by this ferrometry. And I explained what ferronomy was. And we showed that the broken gauge field led to the it'll never catch on, ferronometric model of the quantum potential. And I hope I've given you some more hope as to trying to find out exactly where this quantum potential comes from. And all of that is built in to Vitiello's discussion of consciousness. Okay, James, I've finished now.
It is amazing. Thank you so much, Basil, for that amazing presentation. I've heard people in the chat saying how your presentation skills, all this excitement you put in when discussing formulas and numbers, and it's
I'm
like,
sorry,
yeah.
I'm sorry, I am excited. I'm still excited.
And that is amazing. That is really fantastic. So thank you so much, Basil.
You're welcome. Has it made any sense?
Yes.
We've heard a yes. Basil, just before we move on, let me just ask you a question, because at the beginning of your presentation, you have said how when Bohm's paper came out, it had a lot of bad reviews. Let's just put them this way.
Yeah.
You know, from board.
Just before you go on, can I tell you, I was told that if I worked with David Bohm, I would ruin my career.
And has it?
It's up to you to do that. I've had a whale of a time, man, a whale of a time.
Right.
So if that's what ruining your career does, have a whale of a time.
No, it hasn't done that then. No, my question for you was this. So since those first bad reviews, do you find that the scientific community is listening to you now?
They're listening to the Bohmian mechanics because it's nice and simple. What I'm doing is really challenging them, even the physics community, because I'm combining general relativity, and curved space times with quantum mechanics. And if you talk to people with quantum mechanics, they've never looked at GR. And I think that's where the demand comes, because we have been presented with the idea that GR is something excruciatingly difficult. Okay, the formalism is it's nasty. You know, you look, how long, I won't tell you how old I am, but you can guess. I was around, I escaped across France with my parents as a young kid in April 1940. That's how, so now you can guess how far back I go. And why was I put that red herring? Because I'm an old man. What was I talking about?
If they're listening to you now.
Oh, yeah. Yes, what I found, no, I've lost the track. What the question was,
General relativity, you were saying.
general. Oh yeah, it was. Oh yeah, thank you very much. Thank you. Yeah, it was. General relativity was very hairy, and in fact, I had to. But I got hold of a paper by a guy called Robert Forward, who wrote General Relativity for Experimenters, experimentalists. And when I read that, I thought, by God, it's blooming simple. So hiding behind all those hieroglyphics are quite simple ideas. And when you get hold of those simple ideas, then you begin to move and realize you can bring general relativity into it. Because the intuition is very, very important in all this. And that's what I try to get hold of and try to get it across. And I try to get across to a general audience because these are important ideas. Because the other ideas mislead us or could mislead us unless we know there's another side of the story. Does that answer your question, James?
I think it does. Yes. Thank
Yeah,
you.
I haven't said why they, but why did they disagree? I don't know. To this day, I do not know why there was so much opposition to that Bohm. It was A-level mathematics. And all I thought we did in physics was take the mathematics and then say, what do these terms in this expression mean? And then we say, oh, maybe I could see that with an experiment. And that's all we were doing. And I thought, you know, it's like Dr. Strange when he's sitting in that big office by himself and nobody's in the room and he's sort of going like this, wondering whether it was his personal hygiene was at fault. And I began to think, well, maybe I'm doing something wrong somewhere here. And I wasted so much time.
So they're still not listening to you, basically.
Well, I wasn't listening to myself.
Right.
Anyway, it takes courage. It takes courage.
Of course.
And you have to have a lot of background knowledge to be able to step off the ladder. And I can do that now.
Well, thank you, Basil, for answering my question. Just before we move on to get everyone's questions, let's hear from Shantina, the chair of this event, see if he has anything for you.
Thank you, James. Yeah, I'll take advantage of this privilege offered to me to ask my question to Basil. Basil, you made some very stimulating remark from me concerning time and talked about like forward and backward derivative. And has that anything to do with, for example, another person who will speak at Pari soon, the transactional interpretation of?
No, this is diffraction. I don't know. I did look at the transactional interpretation some time ago, and I didn't feel it was right. There's a feeling, remember? I didn't feel it was for me. Mm-hmm. Because it was going against the particular feelings I can. Is that your photograph there?
Leaving aside the transaction interpretation, your remark about how time comes into the picture here.
Yes.
I'm interested in that.
Well, you need to go to, I didn't put it on my transparencies. When you look at the recording, you will see a list of references. And in there, I've got a paper called On the Theory of Moments. Okay. And if you look at that theory, I actually developed the idea that Giuseppe Vitiello hinted at in his talk, namely that we now have got non-locality in time as well. Okay. Mm-hmm. So that those 2 points are difference between T1 and T2 are the two, T plus and T minus are the 2 times. And when you put that in, you then find that you have the mean time and the time difference. And if you build that into the mathematics, you then see that you have these blobs are actually moments in time. They're the now that he was talking about. So the now is not a localized now. It is more a generalized idea of now in a more ambiguous sense. But the ambiguity is coming in because of the non-commutative algebra that we're playing with. So if you want to try and pin it down, you have to look at that algebra very carefully.
Has
So
that any impact on the issue of determinism?
Oh, I don't know. I don't know, Shantina. Please, could you look at it? Because look, although I show off by using Fichte and I'm not a philosopher. I find their arguments very, very slippery. But that's because, you know, because I'm the under end. I've got this mathematics, which a lot of philosophers do not have a grasp of. And I'm using that all the time to keep me on the straight and narrow. So I find it very difficult. What is it? Well, I don't know, you see. I'm leaving it to you, Shantina. Examine the mathematics and tell me whether it's deterministic or not.
Thank you, Basil.
I'm sorry to put it back on your shoulders. Something very strange. It's a different way of thinking. And if you want to know about that, the nearest I get connections with is Ilya Prigogine. Because I had some correspondence with Prigogine, and the mathematics I'm using is the same as the mathematics that he is using. Only you won't recognize it from what I've told you today. But if you want a private lesson, just give me a call.
Great. Thank you.
Thank you, Shantina. And Basil, I'll try not to take offense on your remarks about philosophers. But anyway.
Oh, it's me who's the rubbish philosopher. I'm the rubbish philosopher. Okay. I'm only criticizing myself.
Okay.
Not you guys out there. I'm take my hat off to you guys.
Well, we'll open it up now to everyone else. We have quite a few hands up already, but just to remind everyone how it works is if you can use the raise your hand function on Zoom, which can be found at the bottom of your screen under reactions, or physically raise your hand or write your question in the chat. We already have quite a few hands up, so we'll take the first one from Annette.
Okay, so first I apologize. I hope sound quality is not horrible. I'm in a 6-hour drive. So I want to thank you, first of all, because your enthusiasm is so positively contagious that even those of us who don't understand mathematics enjoy it. And sorry about that. I didn't mean it was giving the directions. Okay, so my question is this. For those of us that are sort of extrapolating what we're hearing to more of possibly social sciences or other things, when you talked about the collective is the wave, not the individual, could you say just a little bit more about that?
Yeah, but the idea is this, you see, that one would, the classical way of, I think, first of all, let me just say that for sociologists or anybody else of other disciplines, do not use classical mechanics or classical physics as your scientific guide. That's the main point I want to get across. There is another way, which is coming, if you want to use the authoritativeness of the mathematics or the science. That's point number one. Now, the individual and the collective. The strange thing about quantum mechanics is when you see that fringe pattern building up, you do it with individuals, one at a time. So the one is going in and somehow it knows already what the others are going to do. So somehow it has some instructions about the collective in its behavior, so that as individually, it takes those kinks in the curves, just where it should be taken. Now this idea of the collective and the individual, really I got this from David Bohm because he did a lot of work, his original work was done on plasmas. And there you find in a plasma, the electrons are tearing about in all sorts of different ways, yet the plasma is behaving in a coherent way. So there is some interesting relation between the individual and the collective. And all I'm saying is in quantum physics, we're seeing that in action. And the way to think about it perhaps is through ferrometry rather than geometry. In other words, it's the movements, it's the relations, how people move in the society. I'm sure sociologists know that if you make certain movements, they signify something.
I'm just making a connection, which I don't know whether it's true or not, but it feels like when you are really in flow in dialogue and when there's collective sense making, you feel that, right? And so it was just a curiosity that, you know, of the interest of David Bohm. He has the science side, and then there's this other stuff that so many of us are attracted to, and it seems like there's similar parallel movements.
It's the same intuition. It's the same intuition. Mathematicians are not specialists. We live in the world with you guys. We have the same feelings, the same problems, the same medical headaches, and so on and so forth. And we have to communicate with people. And so but it's trying to get that, I don't know how to put the intuition, the sort of the reading between the lines. Forget the bloody lines, read between them. I'm sorry.
Thank you.
Thank you so much.
James, I'm sorry. Please, if anybody gets offended with my language, please bleep it out.
Yeah, sure. No, I was only joking before, Basil, don't worry. So yes, the next question will come from a physical hand. Michael, who's wearing a blue hat.
Yes, Bohm used the expressions implicate order and explicate order. Now the noun order kind of goes back to the prior question on determinism. I know Basil felt philosophy is a slippery slope. Can you tell us, by use of the noun order, did Bohm believe that we live in an intentional universe different from the quantum physics notion that it's all random events in time and space, absent meaning, purpose, intention? It's this notion of intention. Does Bohm's work lead to the conclusion that we live in an intentional universe?
Yes, very much. I can answer with one word. That was his idea. He did not, his idea of order was really remember when I started with him, he'd done his 1952 work and had moved on, written his book on chance and causality. And in chance and causality, you can begin to see the idea of the implicate order emerging as a criticism of the 52 work. Okay. And then and he was moving on to this idea that all is progress. It's Heraclitus, all is flux, all is process. So his order was not to be taken as a noun, but as ordering. And so the universe was ordering itself. Did it have a purpose? I don't know. That was always the possibility. But he rejected the cold determinism of classical physics. It was much richer than that. And in fact, he even thought that you could regard quantum mechanics as in some sense organic. It's the same thing that Whitehead was suggesting, that it really is an organic process. Otherwise, you wouldn't get the evolution coming out. You wouldn't get it. Evolution by just random variable it's not going to work. There is something structurally stable behind the unfolding process. And it's that which people like René Thom with his catastrophe theory was trying to get hold of. And we were very interested in that idea. And in fact, David Bohm also had another order, not only the implicate and the explicate, he also had the generative order. And you'll see the generative order in his book on science, order and creativity, which he wrote with David Peat. And that section, or that chapter, I think illuminates this idea of how he was looking for creativity in nature. So it's not the mechanical determinism. That's why he didn't like Bohmian mechanics. Does that answer your question?
Yeah, from what I understand what you said, I mean, it's deterministic, but can this is my word, it would kind of be like a flexible determinism. And is that a way to approach your idea of creativity?
Although we're in nature, what we're doing is we're trying to say something about nature. And remember, Korzybski always says, whatever you say it isn't that. Yep. So if we say it's determinist, no, it's not quite, because there's this extra flexibility going in there this between the lines, something is moving in a creative way. And nature is of that ilk, would be David Bohm's.
So you're saying laws of nature can change, they're not immutable.
Oh, absolutely. Well, John Wheeler was quite happy with that. Expanding universe, maybe the laws change. We always use the cosmological principle, the principle that Bondi introduced. That is, we assume the physics here and now is the same as the physics over there and then. That's the cosmological principle that's built into all our science. People have said, well, what happens if it isn't like that? And that's then speculating.
Okay, thank you.
Great. Oh, really, really interesting. Thank you, Michael, for your question. The next will be from Nancy.
Thank you. I'm kind of hanging on by the very tips of my fingers. So my question may be totally stupid, and if it is, that's okay. Just tell me, I won't feel bad.
No question is stupid.
I've been trying to understand what the quantum potential is. You know, not the mathematics about it, but just what it is.
It's a new.
Okay, I was thinking it was when you have the double slit experiment, it's what pushes the quantum particle out of the straightway and into a path that makes it look like waves when it reaches the end. But now I understood you said that that's the osmotic momentum. So what then is
I'm sorry.
Experiment. What is the quantum potential?
First of all, a quantum potential is just a different quality of energy. First of all, okay, a different quality of energy. And you can certainly look at the two-slit experiment the way you're looking at it, that it is the force. But if you bring into if you know a little bit about general relativity, okay, well, this is the difficulty, because
no, that's okay. I do
have
physics. It's a long way back there, but I do have physics.
But it's telling you that the geometry changes, and therefore it's the geometry that is somehow set up by putting the slits in the position, putting the piece of apparatus, putting in the it's the whole arrangement that is changing the ferrometry, or the geometry, if you like. Okay, so that then the electron is just doing what comes naturally.
Okay.
It's the same as the light ray going past the sun and being deflected It's not that the sun is pulling it, it's that the geometry has been changed around it, and the starlight is doing what comes naturally. It's following the geodesics.
Have they ever done 3 splits?
Oh yes, yeah, we've done 3, 4, 5. There's an industry now where computers can do all these calculations. You get giddy looking at them. I'm sorry, it's good to have them there. It's good someone wants to do them, because you can just quickly look at it. Oh yeah, that's ghastly, right? Move on.
Okay.
Saves you a lot of problems to say, I wonder what it looks like, because now you can see it.
Okay. Thank you.
Thank you, Nancy. The next question will come from Jonald.
Originally, Bohm started with a Schrödinger equation, and then he used the Hamilton-Jacobi equation sort of to extract the quantum potential. So as I understand it, the Hamilton-Jacobi equation is it's a classical equation that sort of paints a particle in its wave-like behavior. So in using the Hamilton-Jacobi equation, the quantum potential was extracted, was derived, and it became the quantum Hamilton-Jacobi equation. So from the way I see your presentation, did you mean that the Hamilton-Jacobi equation is not necessary for the quantum potential to come out? For example, if you carry through the Dirac equation, if you carry through the Pauli equations, carry through them, the quantum potential will arise naturally, and you don't need really the Hamilton-Jacobi equation to extract the quantum potential.
No, you're right. The classical physics is wrong in this domain. Okay, so what we have to do is to find out what the real theory is, i.e., taking quantum mechanics as the basic theory, and then trying to see how classical physics emerges from that theory. That's the logic of the argument. When you're teaching it or presenting the ideas, everybody knows about the classical physics. So it looks as if you're starting from classical physics, but all you're doing is showing the difference between quantum physics and the classical physics. And so you suddenly see quantum mechanics is telling you that there is this extra quality of energy which is not in the classical domain or in classical mechanics. It's something new. Okay, and it's coming in a way very similar to the vector potential in the electromagnetic theory. So it's not novel, but it's looking at those things in a very different way. Does that help?
Yeah. Thank you.
Great. Thank you very much, Jonand. The next question will come from Katrina.
So Emily talked last week about context and how important context was. And when you were talking about how there was the equation and people want to delete the quantum potential energy, that my first thought was, that's the context. That's the field. Like, you can't delete the context because we're not in a vacuum. And then when you had the picture of the block and you had like our imagining of that particle and then the kinetic energy, and oh, here's all the arrows going this way, but in his picture they were going this way and sideways, and I instantly had this vision of like a football field filled with thousands of people that were already there. Like, that's the quantum field, that's the context. And then this one thing happened and they all just went, you know what I mean? But they're already there. Like, we think that it's us doing everything, and it's sort of in context of what Annette asked about, because I'm more of the philosopher, is like, we don't work in a vacuum, and all of our calculations are wrong in life if we don't consider the fact that we're working within a quantum field. It's like, everything's wrong, right? So I don't know if I'm...
No, that's absolutely right. And I was actually supporting very much Emily in her attempts there, because it is the collective. I've been calling this thing the collective, but it is really the context. What gives rise to the collective is the context. And we have to understand how the context arises in different situations. I think she was saying it's not as simple as you think it is. The quantum theory context is different from what one would normally expect as a, I forget she used it somewhere. Sorry, I'm very bad at remembering what people said. But the point was the context was then hidden in what we were seeing. So it doesn't look as if the context is there,
Right.
but it is. And she was saying that somehow looking at the Bohm model, you could begin to see in what way it was different from the way we normally understand the notion of context.
Yeah, I just want to actually ask one other thing, or I guess I'm not really asking questions, but and Shantina may know better about there's an idea of Wu Wei in Taoism. And the idea is like doing nothing, yet everything gets done. And again, I have this football field, and all of a sudden something happens and all the people are, all the particles are suddenly shifting. And a lot of the idea in Wu Wei is you listen kind of to the quantum field, and then you just go with the flow. Like it's sort of the opposite thing. We think it's all about, no, I make the effort and I affect the field. But what if the field shifts?
No, you're dead right. The field affects us. We think we are isolated, but we're right in the middle of this. And we're being influenced by all these features around in all sorts of subtle ways.
Yeah. Thank you so much.
Okay, you're welcome.
Thank you, Katrina. The next question will come from Mike, who's wearing a black shirt. That's why there are many mics. That's why I'm describing.
Yeah,
people are wearing.
Make sure his mic is on. Oh, he's on.
Yeah, thank you very much. Yes, thank you, James. Yes, thank you. Too many mics, but at least this one has his mic on. Yes, Basil, that was fascinating and very, very clear. And obviously, I've heard you talk about these things on previous occasions over the years, but it seems to me that an awful lot of the ideas that have been bubbling away for a very long time now really are starting to converge and come together beautifully. Just two quick remarks. One of the things that you were talking about, the connection between the things which Emily was saying last week about contextuality and the non-contextuality of the quantum formalism, and the point I'd like to underline there is that the mathematics in terms of which this contextuality and the quantum formalism shows up, which she was talking about a little bit, is also very intimately related to our understanding of the way that local and global structures fit together in the mathematics, and particularly the way in which one can go from global to local, or from local to global, in the context of geometry and topology. And the interesting thing about your notion, your broadened notion of geometry, dynamical geometry that you're calling ferrometry, is that it precisely does display in the same way the kind of obstructions which arise when we try to go from local to global, or from global back to local, without taking account of the way that the dynamics is in fact shifting, if you like. It's spreading out. For instance, the very notion of point or is changing our notion of what it is for something to be a localized object. You brought out very nicely in what you said about Morris's notion of the quantum blob, the way that this involves breaking with the old notion of punctiform elements of absolutely determinates of atomistic points of some kind, starting points in geometry, but perhaps also even breaking with the notion of the now, of the kind of some absolute notion of now in the temporal context. Sorry to burble away. I just wanted to say one other thing quickly, which is that you made the very interesting point about obviously one of the great novelties that was involved in the introduction of the idea of the quantum potential or so it seems to me. And I think one of the reasons that people were so resistant to it, and still are to a great extent, but certainly were very resistant to it at the time that it was first introduced, even though it had in fact been there, in the shadow of it was already there in the formalism which these people had been discussing, you know, in the 20s and 30s and 40s, was precisely that it did break with this underlying mechanical picture of reality. It made room for the kind of return, if you like, the re-entrance of ideas which had appeared to be completely ruled out since Galileo Newton, including the old Aristotelian ideas of formal and final causation, which seem to have a very natural kind of context in biology particularly, and in our understanding of the distinction between, or well, what it is in fact that distinguishes mechanisms from organisms. I'm sorry, there's a lot there, but I was wondering whether there's any of that that resonated with you.
Well, well, first of all, Mike, the recent searches that our group have been going through for the 1920s and 1930s, there was not a resistance to the quantum potential. It was discussed openly. They didn't understand where it came from, and I can quite understand why they didn't understand, because, you know, it's been a long search to see that it's actually arising out of broken symmetry. They knew nothing about gauge symmetries at that stage. No, something seemed to have happened that when everything started up again after the Second World War, everything that was before that was completely forgotten. And somehow, maybe it was in the politics, because, you know, David Bohm had that tremendous problem with McCarthy in America, and he had to leave America and settled in Brazil. That was at the time that the paper that he wrote in '52 appeared. So he was sort of then cut off. And I wonder how much politics is involved.
Yeah, I mean, clearly there was an external, if you like, kind of sociology of knowledge and political and cultural context, which is certainly very well worth investigating. But I can't help thinking that it's the basic metaphysical insight that this notion of quantum potential is actually carrying us outside the mechanistic worldview. It's the point that he made in the 1957 book that he was already hinting at strongly there, when he said that, you know, if you pursue these ideas in the direction in which they naturally lead, you see that our fundamental rock bottom kind of ontological understanding of the universe cannot be a mechanical one. I mean, as it were, mechanics cannot be, the fundamental underlying ontology cannot be a purely mechanical one.
Yes, but Mike, that's what Bohr was saying. Bohr would recognize that. But
well, except Bohr didn't want to talk about ontology at all, didn't he?
Well,
he just wanted to talk about what you can or can't know and what you can or can't say.
That was one of the reasons why I took up this long search, was because I didn't believe that we're not allowed to ask these kind of questions.
Sure. Yeah.
Sorry,
and if you like, the other tradition in foundations of physics, which is in some sense orthogonal to these ideas of exploring the deeper structures, particularly in phase space, and the significance of the algebraic structures that you've been exploring, which has actually turned into a huge bandwagon, I think, in fact, with rather disastrous effects for the foundations of physics, which is the program of trying to treat the existing, you know, mechanical formalism, the unitary linear quantum mechanics, as sticking with the mechanical ontology and really trying to make it an absolutely universal ontology, which is what has led to the whole, you know, many worlds interpretation, the Everett picture. I think that can be seen as stemming from an absolute determination to hang on to the idea that, in some sense, mechanics is the end of the story. Whereas the take-home message of Bohm's work and of your own work seems to me, well, precisely working out the wider ramifications of the recognition that mechanics is not the end of the story.
Yep. Well, thank you, Michael. I quite agree with you. And there's a good reason why we would agree with each other, because we've been talking about these things for quite a number of
years. Which is why it's a bit wrong for me to monopolize the discussion. I apologize to all the other people here.
I'm glad you do, because you put things in a way which supplements or complements what I'm saying.
But it has been it's been a privilege listening to you, as always.
Thank you, Mike. It was very interesting discussion. We'll take the next question from the chat, actually. Gary, would you like to ask the question yourself, or you're muted at the moment?
Yeah, why don't you just read it? That's fine.
Yeah, sure. Okay. I mean, if you want to read it, that's better. But I can read it for you if you like.
Yeah, go ahead, James.
Let me just find it. Okay. So it reads, Bohm implies in his paper, Time, the Implicate Order, and Pre-Space, that space-time emerges as a constructed container for phenomena as they are detectable in the explicate order. So that space-time does not exist in the hidden implicate order. What does this imply about the degree to which space-time itself is a construction, and that the underlying reality of the implicate order of the quantum world is not a realm of space-time? As a work of Nima Orkani, Ahmed and Associates on the amplitudron tends to imply. I'm sorry if I didn't read the words properly.
That's fine.
Okay, yeah, well, let me tell you the story. When I began working with David Bohm, I had the privilege, I'd done my PhD in solid state physics, and I'd always been fascinated by some of the questions in quantum mechanics. And I was fortunate enough to get a position with David Bohm in Birkbeck College. And who should be there at the same time but Roger Penrose? And we used to meet together, very inspiring days. And what we were talking about, we weren't talking about quantum mechanics per se. We were talking about really, I think I mentioned this in Emily's talk, that we were talking about how to quantize gravity. And I think that's one of the things that she wished she was trying to get towards. And I said, good luck to her. Because that's exactly what we were dealing with in the 60s, wasn't it? My God, that's a long time ago, isn't it? In the 60s. So what were we saying? We were backed up by Roger Penrose, I think, at that time. And the idea was that if we stuck with relativity, tells us that somehow space-time is not a stage, but in which we dance, but rather matter and space-time co-determine each other. So what does that mean? That means we must go before. We can't put everything in space-time anymore. If we try to take space-time as the G mu nu, the metric tensor, for example, if we try to quantize that, what we'd find is that we'd have quantum fluctuations. And then the question is, what does it mean to have a space-time in which your measure is fluctuating? Now, maybe when you're drunk, you experience that kind of space, but certainly not when you're sober. So we've got to say that we've got to start somewhere else. And the big question was, where do we start? David Bohm's idea was we start with this notion of structure process, which I have tried to start with, but I find people find it very vague and nebulous, and really it's very difficult to say what it is. It's like, unfortunately, it's very much like a word, whenever we're talking, we always have a minimum vocabulary. That is a group of words which we cannot define in terms of other words without going round and round in circles. So that's not helpful. But then what Roger was saying was, Well, look, let's use quantum mechanics. Let's use the way we combine spin systems together to see if we can get angle, for example, was in the very simple model that he was using at that stage. And that was his spin networks. And then when he found the spin networks coming out, what you could do is when you averaged over this in a very strange way, which was not clear, you found space-time emerging. So then the idea was that you don't start with space-time, but you have to have some deeper process from which space-time emerges. And this is where David Bohm's implicate order, as you say, comes in. It comes in through, Gary, through the, just seeing your name again, I forgot your name a minute. It comes through the idea that implicate order is not in space-time.
Right.
That you actually are organizing that your experiences, you're trying to explicate space-time in that.
So that space-time as part of the explicate order is our sort of our instrument panel, right?
That's right. That's right. That's right.
With physical actuality, but that the reality of quantum, of the quantum world, is not at all space-time per se.
No,
right?
no.
It's pre-space is what I mean. That the term that that Bohm used was pre-space. In this,
yeah, we used a lot of that pre-space. Yeah. And then we replaced that with the idea of the hollow movement, which
right.
was mentioned at some stage. But that was actually mentioned in a paper that David and I wrote very early on, where we used this idea that it was combining movement with Bohr's idea of wholeness. So then a hollow movement, which is obviously a way of putting the two pieces together to say there is a global movement of some kind. And here again, movement, not movement of something, but movement in the
as a process,
as a very ferrometric idea. I mean, I didn't know the word then, otherwise we would have really built on it from that point on.
I think our nominalistic minds force us to think about things.
Right? Of course, because we get by thinking of things, and we find non-commutativity very mysterious. But sorry, if you want a cup and it's in a cupboard with a door, you've got to open the door first before you take the cup out. So, you know, we are actually always in our activity. We're always doing these kind of things, and we were looking for the invariance, and that's where the explicate order comes in, because we're looking for this invariant which we can get hold of and make a picture of it, like the gestalt of the old lady and the young lady, which I sometimes show.
Thank you.
We are constructing that.
Yeah. Can I just come in super quickly to say, of course, another reason that for this nominalistic bias is that at least in Indo-European languages and in Western culture, of course, nouns are our fundamental category for kind of articulating our experience of the world. It's very interesting that there are cultures in which verbs are actually more fundamental. And in the so-called feature placing languages, where you don't say there is a table there, but you say it is tabling around here. I mean, that's not quite right, but that's essentially the idea that.
Yeah. Right. David and I went.
Roy Little Bear will be talking about that in the Black.
Oh, I was just going to ask. I was going to say it's a great pity he's not here at this moment, but yeah.
But David and I did talk about this, and we got to the stage where we're so conditioned with our Western way of thinking that we were just translating verbs into nouns, and the whole thing just collapsed. There's something deeper involved, which I think Little Bear will be explaining to us or giving us an account of. You're quite right.
Well, thank you, Gary, for bringing that question forwards. And yes, Leroy Little Bear will be part of the second part of the Beyond Bohm series, where there'll be basically a panel discussion with him and his colleagues. So yes, unfortunately, we've gone a little bit over, so I'm guessing we can't really take any more questions. I'm really sorry for all of those that have their hands up. But Basil, do you have any final closing remarks for us?
No, just thank you very much for being patient and listening to my nonsense.
Well, thank you, Basil, because you've made your topic, even if it was math, sound really, really interesting, and it was very interesting. So thank you very much, Basil, for that. Thank you for your presentation. Thank you for all of you for joining us, for asking your question and keeping the discussion going. So just before we all go and have our dinner, lunch, or breakfast, just like to invite you all to tomorrow's session, where we'll have Paavo Pilkkanen on understanding the nature of reality and consciousness, Bohm's philosophical project. So I hope to see you all tomorrow to that. I also wanted to remind everyone that we have the Sutra group going on. It's basically our online forum where we'll be able to basically discuss the ideas that we've been exploring in this series. If you haven't received the link or you want to know more about the Sutra or for anything else, you can contact us via our website or Facebook, Twitter, Instagram, all of social media, or by email. To contact me, you can email james@parcenter.com, or to contact Eleanor, the organizer, eleanor@parcenter.com. Thank you all again for joining us, and we'll see you again soon here at the Party Center.
Thank you, James.
Thank you. Thank you, Basil.
Basil, thank you, James.
Thank you, Basil.